Welcome, everyone. Today, we are diving into the fascinating world of marine biology to explore a remarkable group of animals known as Chondrichthyes. If you have ever been captivated by the silent, graceful glide of a shark or the majestic wingspan of a manta ray, you are already familiar with these incredible creatures. In this lecture, we will uncover the unique biological engineering that makes them such successful ocean predators. To truly appreciate how these animals are built, imagine you are designing a submarine. But instead of using heavy, rigid steel, you construct it using a tough, flexible, and lightweight plastic. This submarine would be incredibly agile, fast, and require much less energy to stay afloat. In the natural world, this is exactly what nature did when designing sharks, rays, and skates. Their bodies are masterpieces of lightweight engineering, allowing them to move with unmatched grace and efficiency in the dense aquatic environment. Now that we have a mental picture of their lightweight design, let us look at what actually makes up their framework. The term chondrichthyes comes from the Greek words for cartilage and fish. Unlike us, or typical bony fishes, these jawed vertebrates have skeletons made entirely of cartilage. This is the exact same flexible, rubbery material that gives shape to your nose and your ears. This evolutionary choice sacrifices some rigid strength, but gains immense flexibility, making them some of the oldest and most successful predators on the planet. Beyond their unique, flexible skeletons, these creatures possess several distinct anatomical features that separate them from other fish. First, they have tough skin covered in tiny, tooth-like structures called placoid scales, which drastically reduce water drag. Second, they breathe through 5 to 7 exposed gill slits that lack a protective bony cover. Finally, they typically feature a heterocercal tail, meaning the upper lobe of the tail fin is significantly longer than the lower lobe, providing powerful downward thrust as they swim. Understanding these physical traits naturally leads us to ask why these animals matter so much to our world. Evolutionarily, they represent a major milestone, being among the earliest living groups to develop jaws and paired appendages, the distant precursors to our own arms and legs. Ecologically, sharks and rays act as apex predators. They sit at the top of the food chain, regulating populations of other marine species to keep the ocean ecosystem balanced. Furthermore, their drag-reducing scales have even inspired human engineering, leading to faster Olympic swimsuits and more efficient ship hulls. Despite their brilliant evolutionary design, these animals face one massive physical challenge in the water. Unlike bony fishes, chondrichthyes completely lack a gas-filled swim bladder. This means they do not have a built-in balloon to keep them afloat, so they constantly struggle against the downward pull of gravity. If they stop swimming, they sink. To survive, they must rely on a massive, oil-filled liver for buoyancy. To truly understand how they avoid sinking to the dark ocean floor, we must look at the fundamental physics of buoyancy. This brings us to the mathematical reality of their survival. When an object is submerged, it experiences an upward buoyant force, while gravity pulls it downward. The net downward force, F, is simply the actual weight of the shark minus the buoyant force. In this formula, the symbol rho sub S represents the average density of the shark's body, and rho sub W is the density of the surrounding seawater. V stands for the total volume of the shark, and G is the acceleration due to gravity. If the shark's density is greater than the water's density, this force is positive, meaning the shark will experience a net downward pull and sink. Before we move on, let us see this with a concrete example. Imagine a great white shark with a volume of 2.0 cubic meters. The density of seawater is 1,025 kilograms per cubic meter. If this shark did not have its special oily liver, its heavy body density would be 1,090. We substitute these values into our formula, subtracting the water's density from the shark's density, which gives us a difference of 65. Multiplying this by the volume and gravity, we get a final answer of 1,274 newtons. Physically, this means the shark is constantly dragged down by a force equivalent to carrying a 130-kilogram weight on its back. Now that we have used this formula to see the immense physical struggle the shark faces, let us understand exactly where this equation comes from. We are setting out to prove how the density difference directly creates this sinking force. We start with the basic physical principle. The net force F is the total weight, W, pulling down, minus the buoyant force, B, pushing up. The weight of the shark is simply its mass times gravity. Since mass is equal to density times volume, we can rewrite the shark's total weight as the density of the shark times its volume times gravity. This gives us the downward component of our physical system. Continuing our derivation, we now look at the upward push. According to Archimedes' principle, the buoyant force equals the weight of the displaced water. The mass of this displaced water is the water's density times the shark's volume. Therefore, the buoyant force B is the water's density times volume times gravity. When we substitute both the weight and the buoyant force back into our original net force equation, we see that volume and gravity are common terms. By factoring them out, we arrive at our final elegant result. This proves mathematically that the sinking force is entirely dependent on the difference in density between the animal and the ocean around it. So, we have proven that a higher body density creates a massive sinking force. This brings us to nature's brilliant solution. To minimize this exhausting downward pull, sharks have evolved massive livers filled with a special oil called squalene. Because oil floats on water, squalene has a very low density. As the volume of squalene inside the shark increases, it acts like internal bubble wrap, decreasing the shark's overall average body density. This biological adaptation brings the animal's density much closer to that of the surrounding seawater, drastically reducing the energy the shark must spend just to stay afloat. Let us see exactly how much of a difference this squalene liver makes mathematically. We take the exact same healthy shark with a volume of 2.0 cubic meters. But now, thanks to the oil, its overall average body density has dropped to just 1,030 kilograms per cubic meter. We substitute this new, lower density into our net force equation. The difference between the shark's density and the water's density has now shrunk to a mere 5 kilograms per cubic meter. Multiplying this tiny difference by the volume and gravity, we get a final answer of only 98 newtons. The shark has reduced its sinking force from over 1,200 newtons down to almost nothing, allowing it to glide effortlessly. Now that we understand the physics, let us look at the complete biological package. In this diagram, you can see the anatomy of a typical Chondrichthyes. Notice the massive, yellowish, oil-filled liver taking up a huge portion of the body cavity. This is the squalene engine we just calculated, perfectly manipulating the physics of buoyancy. Toward the back, you see the asymmetrical heterocircle tail, providing lift and thrust. Near the head, the 5 exposed gill slits are clearly visible without any bony cover. And in the magnified inset, you can see microscopic placoid scales that reduce drag. Every single feature here is a highly refined evolutionary adaptation. We have covered a lot of ground today, so let us summarize the most important ideas. First, Chondrichthyes are a remarkable class of jawed fishes, defined by their lightweight, flexible cartilage skeletons. Second, their unique anatomy, including drag-reducing placoid scales and exposed gills, makes them highly efficient apex predators. Finally, and most importantly, because they lack a swim bladder, they rely on a massive, squalene-rich liver to lower their body density and counteract the physical force of sinking. You have now seen firsthand how biology perfectly intertwines with the laws of physics to ensure survival in the deep ocean. Great job following along.